Hello friends, welcome back to the series of online lectures for AMVI Mains examination, a complete guide. Today in this lecture we are going to talk about entropy. So in this lecture we will be discussing about following points. What is entropy, properties of entropy, then entropy change and its calculation, and at last we are going to discuss the entropy and thermodynamics. So let us start with the what is entropy. Entropy is one of the important concepts that students need to understand clearly while studying. More efficiently, entropy can be defined in several ways. So, the concept of entropy basically talks about the spontaneous changes that occurs everyday phenomena in the everyday phenomena or the tendency of the universe toward the disorder. Generally, entropy is defined as a measure of randomness or disorder of a system. Now, the concept of this entropy was introduced by a German physicist named Rudolf Clausius in the year 1850. Apart from the general definitions, there are several definitions that one can find for this concept of entropy, and the two definitions of entropy that we will look here are the thermodynamic definition and statistical definitions. From a thermodynamic point of view of entropy, we do not consider the microscopic details of a system. Instead, entropy is used to describe the behavior of a system in terms of thermodynamic properties such as temperature, pressure, entropy, and heat capacity. This thermodynamic description took into the consideration that the state of equilibrium of a system. Meanwhile, the statistical definition, which was developed at a later stage, focused on the thermodynamic properties which were defined in terms of statistics of the molecule motion of a system. And entropy is a measure of the molecular disorder. So this statement is very important about this entropy. Now let us discuss the properties of entropy. This entropy is a thermodynamic function. Then it is a state function. It depends on the state of the system and not the path that is followed. Then another property is that it is represented by S, but in the standard state it is represented by S dot. Its a SI unit is joule per kilomole and its CGS unit is calorie per kilomole. Entropy is a extensive property, which means that it scales with the size or extent of a system. Now here, one thing we have to note that the greater disorder will be seen in an isolated system. Hence, entropy also increases. When chemical reaction takes place, then if reactants break into more number of products, then entropy also get increased, and a system at higher temperature has a greater randomness than a system at a lower temperature. From these two examples, it is clear that entropy increases with a decrease in regularity, and for that entropy order is I have shown as gas having more entropy than the liquid and solid. Okay, then let us highlight discuss about the entropy change and calculation. Now during entropy change, a process is defined as amount of heat emitted or absorbed isothermally and reversibly divided by the absolute temperature. And the and the entropy formula is given as delta S is equal to Q reversible isothermally divided by T. Then total entropy change we can calculate by using this formula. Delta S total is equal to delta S surroundings plus delta S system. If the system loses an amount of heat, that is Q, at a temperature T1, which is received by the surroundings at a temperature T2, so delta S total can be calculated by using this formula. Delta S system is equal to minus Q divided by T, and delta S surrounding is equal to Q divided by T2. And finally, we can calculate delta S total is equal to minus Q divided by T1 plus Q divided by T2. So, and again in that, if this delta S total is positive, then that process is spontaneous, and if delta S total is negative, then that process is non-spontaneous, and if that delta S total is 0, then process is at equilibrium. So these are the conclusions where we have got from the this entropy concept. Now here point to remember is that a spontaneous process is thermodynamically irreversible, correct? And another point is that the irreversible process will attain equilibrium after some time. So these 2 points we need to remember. Now let us discuss the entropy change during the isothermal reversible expansion of a ideal gas. As we know that delta S is equal to Q reversible isothermal divided by T. According to first law of thermodynamics, we can write equation delta U is equal to Q plus W. But for the isothermal expansion of an ideal gas, this delta U is equal to 0. So Q reversible is equal to minus W reversible, because we are getting this equation from the first law of thermodynamics. And for W we have the formula, that is nRT ln V2 divided by V1. Therefore delta S becomes nR ln V2 divided by V1. Okay, so this is a formula for entropy change during the isothermal reversible expansion of an ideal gas. Let us continue with entropy change during reversible adiabatic expansion. Now for an adiabatic process, heat exchange will be 0, that is Q is equal to 0. Therefore reversible adiabatic expansion is taking place at a constant entropy, so it is called isentropic process. So mathematically I can say Q is equal to 0, therefore delta S becomes 0. Even though reversible adiabatic expansion is isentropic, but irreversible adiabatic expansion is not isentropic. So this point we need to note down. So this delta is not equal to 0. Now let us discuss the entropy and thermodynamics. Now according to concept of entropy and spontaneity, the second law of thermodynamics has a number of definitions. The second law of thermodynamics has a number of definitions, and out of that, first is the all naturally occurring spontaneous processes are thermodynamically reversible. Then the complete transmission of heat into work is thermodynamically not feasible without wastage of a certain amount of energy. Then another definition is that and this is very important, that the entropy of the reverse of the universe is continuously increasing. And from this statement, there is another statement of the second law of thermodynamics, that is, the total entropy of an isolated system never decreases. Also, the total entropy change is always positive, and the entropy of a system plus entropy of surrounding will be greater than 0. Okay, and the equation I have shown here. So this is about second law and entropy. Now let us discuss entropy and third law of thermodynamics. So the entropy, according in the third law of thermodynamics, the entropy of any crystalline solid approaches to a 0 as the temperature approaches absolute temperature. So this is statement of third law. The entropy of any crystalline solid approaches to a 0 as the temperature approaches absolute temperature. Now it is because there is a perfect order in a crystal at an absolute 0 temperature. So the limitation of this law is that many solids do not have 0 entropy at absolute 0. For example, glossy solid containing a mixture of isotopes. So these are the examples of the solid which do not have 0 entropy at absolute 0. So this is about the entropy and thermodynamics. Now let us take a revision, or here I have shown some remarks about the entropy. In that, first is that entropy change of the system will have the some sign as a heat transfer in reversible process. Then processes can occur in a certain direction only, not in just any direction, such that the entropy generation is greater than or equal to 0. Then entropy is a non-conserved property, and there is no such thing as a conservation of entropy principle. Another point to be to notate that the entropy of a universal is continuously increasing, as all the processes happening in the universal are irreversible. And the important is that the performance of engineering systems is degraded by the presence of irreversibilities. Entropy generation is a measure of the magnitudes of the irreversibility present during that process. So the whatever the entropy change is there, it is caused by heat transfer and irreversibilities. So this point to be noted. Another point or remark is that heat transfer to a system increases the entropy, and heat transfer from a system decreases the entropy. The effect of irreversibility is always increases the entropy. In fact, a process in which heat transfer is out of the system may be so irreversible that the actual entropy change is positive. So in that again, friction is one of the source of irreversibilities in a system. The entropy change during the process is obtained by integrating the ds equation over the process, and the inequality is to remind us that the entropy change of system during an irreversible process is always greater than this cyclic integration from 1 to 2 dou q divided by T, and it is called entropy transfer. That is, some entropy is generated or created during an irreversible process, and the generation is due to entirely to the presence of irreversibilities. And the entropy generated during the process is called entropy generation, and it is denoted as S generation. And we can remove the inequality by noting the following, that is, delta S system is equal to S2 minus S1 is equal to cyclic integration 1 as a 1 to 2 dou q net divided by T plus S generation. Here S gen is always positive quantity or 0. And its value depends upon the process, and that is and thus it is not a property. This S generation is 0 for internally reversible process, and the integral which is I have shown here is performed by applying the first law to the process to obtain heat transfer as a function of temperature, and the integration is not easy to perform in general. So these are the some remarks about the entropy uh, which are very useful for the during the examination. So this is the source which is I used for this lecture. So this is about the today's lecture. Please stay tuned for more videos regarding this RTO AMVI mains examination, and don't forget to subscribe to our YouTube channel and press the bell icon to receive notification regarding more videos from this lecture series. Thank you very much.